Hello, everyone. My name is Dan Jonas Roach, and I am the news editor here at the Architects newspaper. I'd like to welcome you all to the Enhancing Sustainability Through Materials and BIM live webinar, a CE Strong webinar series powered by the Architects newspaper. This webinar is sponsored by Vectorworks. This program is registered with the AIA CES for continuing professional education. Questions related to specific materials, methods, and services will be addressed at the conclusion of this presentation. This webinar is recorded and can be easily replayed when re-registered on the same webinar registration page. Please allow 7 business days to process Certificate of Participation and AIA credit reporting for this presentation. At the end of this course, participants will learn to list the 7 core principles of sustainable construction, explain how high-quality materials lead to the health, safety, and welfare of occupants, a reduction of embodied carbon and less waste, describe how materials and BIM software provide a systems approach that leads to more efficient buildings. Recognize how high-quality materials and design can lead to cost savings and a reduced carbon footprint without sacrificing aesthetics or occupant comfort. We encourage you to ask questions using the Zoom Q&A button found at the bottom of your Zoom window. Now, I'd like to introduce you to today's presenter, Sarah Walker. Sarah Walker is the Senior Architect Product Specialist at Vectorworks. Her passions within architecture are design, planning, mapping, visual scripting, and computer rendering. In her spare time, she enjoys creative writing and practicing Bikram yoga. Remember to please leave your questions for Sarah in the Q&A window. Without further ado, Sarah Walker.
Sustainable construction and green building are terms and concepts that have gone from novel to trendy to mainstream in the past few decades. They're very broad concepts that encompass a great deal of different strategies, methodologies, and approaches. They probably have specific connotations for each of us. Today, I'm going to use a definition I found in an article titled Greening Project Management Practices for Sustainable Construction, written by Laura Bradley Robichaux and Vital Anand-Tatmola. They define green building as a philosophy and the associated project and construction management practices as efforts that seek to 1. Eliminate or at least minimize impacts on the environment, 2. Enhance the health and well-being of occupants, 3. Cultivate economic development for both developers and whole communities, and 4. Apply life cycle approaches to community planning and development. In other words, building practices that seek to minimize negative impact and cultivate long-term positive impacts on all stakeholders, occupants, surrounding communities, and developers. In this same article, the writers define 7 core principles of sustainable construction. The first is reducing resource consumption. This can refer to material resources in 2 ways. First, using or specifying longer-lasting materials means that materials need to be replaced less often and therefore result in less consumption overall. Another way to think about this, in terms of material resources, is to focus on less material waste during construction. This takes planning and coordination to achieve and can be made much more feasible through the use of building information modeling, or BIM software. Reducing resource consumption can also refer to energy resources, where specifying more efficient systems means less overall energy usage. This project uses fiber cement panels for the facade, a material that is very durable, weather-resistant, and longer lasting than many other facade materials. The lifespan of these panels is at least 50 years. In order to reduce material waste, it would be important to model panels like this, so it would be possible to both plan for the correct number of panels and to optimize panel seams. This can even be done with sheets of drywall for interiors. Drywall sheets are typically 4 feet by 8 feet and are laid vertically on walls, but sometimes the shape of the space might mean that arraying them horizontally would be more efficient. These kinds of strategies can only be implemented with detailed BIM models. The second core principle of sustainable construction is reusing resources. This means specifying materials that can be reused or recycled with minimal processing. This reuse can be thought of as both the source of the material and as the destination. Renewable energy resources can also fall into this category. This project can be categorized as reusing resources because it's an adaptive reuse of an existing building. An old factory in Utrecht was largely conserved and converted into a mixed-use space for multiple building types. The third is using recycled resources. Specifying products that contain recycled content contributes to a circular economy. And using reclaimed wood, metal, or stone can serve as an aesthetic statement for a project. This residential project by Jeremy Levine Design uses reclaimed wood for the ceiling, adding warmth to the interior space. Besides wood, another material that is important to specify as recycled is steel. Steel is relatively easy to recycle, and the recycling process does not diminish the strength, longevity, or usability of the material. Manufacturing recycled steel uses 5 times less carbon emissions than virgin steel. The fourth principle of sustainable construction is protecting nature. This means reducing the overall impact of your design on the environment. Not only is it important to think of the site of your building, but also the environmental impact of harvesting and transporting the materials to construct it. The designers of the project, of this project in particular, worked hard to minimize this house's impact on its site. The house was raised on piles, so there was minimal disturbance to the ecology of the site. The physical impact of the structure is only 60 square feet. The fifth principle is eliminating toxics. It's important to specify materials, finishes, sealants, etc., without volatile organic compounds, or VOCs. VOCs are a broad array of mostly human-manufactured chemicals that off-gas into the environment. VOCs are one of the biggest contributors to poor indoor air quality and are very ubiquitous. They can be found in paints, varnishes, adhesives, composite wood, and foam. Common VOCs include formaldehyde, toluene, benzene, and ethylene glycol. Another group of toxic compounds are phthalates. Phthalates are chemicals that make plastics more flexible and resilient. So these compounds can be found in PVC, carpet, vinyl, and upholstery. They can also be found in typical flooring and wall coverings, acoustic ceiling surfaces, waterproof membranes, and electric cord insulation. VOCs and phthalates are hard to avoid completely, but more and more non-toxic building and finish materials are becoming available. There are lots of options for zero VOC latex paint, as well as mineral paints such as clay paints and milk paints. Other non-toxic material options include formaldehyde-free plywood and natural gypsum drywall. The sixth principle of sustainable construction is applying life cycle costing. It's important to think of not only the impact, but the cost of a building from cradle to grave. Cradle to grave is a life cycle assessment term that implies the life of a building from the birth or sourcing of its raw materials through the manufacturing, transport, and installation on the site, as well as throughout the building's life cycle and the energy it uses until the building is decommissioned. Life cycle costing gives the true cost of a building. Greener materials and energy systems are often more expensive at the outset, but end up costing less over time for a multitude of reasons. Being able to calculate the true cost of a project is not only useful to convince stakeholders, but also to add more context to the design. With this added context of time, it's easier to find ways to optimize buildings and get the most out of the space. The seventh principle of sustainable construction is focusing on quality. As I just mentioned, higher quality materials, though more expensive at the outset, often cost less in the long run because they last longer and work better. High quality materials and materials that are free from toxics have less of an environmental impact when being manufactured, while still being high performing. Natural raw materials and methods are often more expensive than chemical treatments and fossil fuel heavy manufacturing. Energy efficient buildings may require higher quality materials to better insulate, and more expensive heating and cooling systems and technologies. Smart technologies, for example, that can be used to monitor and optimize energy usage, are an additional cost to install and incorporate into building systems. However, this greater upfront cost can be translated to savings through time, as higher quality materials are replaced less often, energy efficient buildings cost less to heat and cool, and energy systems that fully or even partially generate their own energy cost much less to operate. Factoring these costs throughout the building's life makes it easier to justify the higher initial cost to clients and stakeholders. Sustainability is all about being thoughtful in design and construction. These 7 core principles, reducing resource consumption, reusing resources, using recycled resources, protecting nature, eliminating toxics, applying life cycle costing, and focusing on quality, all require attention to detail, and while still thinking about the project from a systems perspective. The quick and easy route is unlikely to be the sustainable one. The sustainable route is not only likely to be the more difficult route, but also the more expensive one. So it's important to make up costs through the efficiency of both the project itself and the design process. It can be difficult to be efficient about sustainable design when information on the true nature and true environmental cost of materials can be incomplete, biased, or obscured. When getting started with sustainable design, the depth and breadth of the design problem can be overwhelming. The US may be behind other countries in standardizing requirements for sustainability, but there is one US-based resource that I believe is both comprehensive and accessible for designers interested in learning more about sustainable design and implementing sustainable practices. That resource is the website architecture2030.org. This website is home to the 2030 Challenge. The 2030 Challenge was established in 2005 as an initiative to reduce the amount of carbon released into the atmosphere by the building industry. The goal is to have all new construction be zero carbon by 2030. The AIA created the 2030 Commitment as a national framework for tracking a firm's progress to meet this goal with simple metrics and standardized reporting. In recent years, however, it's become clear that 2030 is not soon enough. In 2015, the Paris Agreement established the goal of limiting global warming to 1.5 degrees Celsius. This was to be achieved by reducing global emissions to zero by 2050, but at our current rate, that's not soon enough. To limit global warming to 1.5 degrees, the world needs to achieve zero emissions by 2040. The building sector makes up nearly 40% of annual global CO2 emissions. More specifically, building operations and energy usage make up 28% of global emissions, and the manufacturing of materials and construction makes up 11% of global emissions annually. These emissions from materials and construction are what is typically referred to as embodied carbon. Because the building sector is responsible for such a large percent of CO2 emissions, it makes sense that we should try to lead the way in reducing our emissions. The 2030 Challenge website offers thought leadership as well as strategies that architects can use to enhance the sustainability of these projects. Within the Empowering the Building Sector section, there's a link to the 2030 palette. The 2030 palette is a free online resource for the design of zero carbon, adaptable, and resilient building environments worldwide. The database contains sustainable strategies for all scales of design, from building scale to regional scale. Each of the thumbnails shown contains information on that particular region or landscape type, as well as strategies for more sustainable building practices on that specific landscape. For example, the Living Shoreline section has an opening statement that states, preserving, creating, or enhancing natural systems such as marshes, beaches, and dunes protects shorelines from erosion. It then follows with strategies for creating these living shorelines. Strategies for enhancing the sustainability and resiliency of cities and towns include heat island mitigation, the targeting of specific new growth areas, creating parks, urban bikeways, urban infill as opposed to sprawl, and retrofitting existing buildings. At the district scale, there are further strategies to improve and optimize densities around district centers, as well as make cities more conducive to walking, biking, and public transit. At the scale of the site, there are strategies and considerations that can be made to preserve ecologies and protect nature at the level of an individual project. And at the building scale, there are multiple design and form strategies for passive heating and cooling as well as daylighting. And in the materials section, there's a database of materials, their embodied carbon statistics, and strategies for reducing embodied carbon in a built project. As I mentioned earlier, embodied carbon is a term for the CO2 emissions from the manufacturing, transportation, and installation of building materials, and it makes up 11% of total global CO2 emissions. This means that for, say, a cubic meter of concrete, there is a number of kilograms of embodied carbon that are released into the atmosphere from harvesting, manufacturing, and transporting that volume of concrete. Basically, every machine powered by fossil fuels that is used in the process of creating that volume of concrete emits CO2, and therefore that concrete is responsible for that CO2. That number of kilograms of CO2 depends on where it comes from, what type of manufacturing process it goes through, and how far it travels. Because of these variables, it's difficult to calculate accurately. Operational carbon is arguably much easier to calculate because energy used by buildings usually comes from only one or two specific sources, and those sources have relatively straightforward carbon emissions. The materials link on the 2030 palette takes you to the Carbon Smart Materials palette page, where there are strategies for lessening the impact of high carbon predominant building materials, as well as strategies for using low carbon alternative materials. I won't talk about every material on this page, but I want to go over a few to show what resources are available. Concrete is the most common construction material in the world. It's responsible for between 6 and 10% of anthropogenic or human activity-related CO2 emissions globally. Portland cement is the primary ingredient in concrete and is responsible for most of concrete's CO2 emissions. CO2 is released by mining equipment that harvests the materials for cement, limestone, silica, alumina, and gypsum, and more carbon is released in the manufacturing process. Manufacturing cement creates carbon in two different ways. First, from the burning of fossil fuels used to power the manufacturing plants, and second, from the process itself. The process of cement creates chemical reactions that also release CO2 into the atmosphere. Because the majority of the concrete's carbon emissions come from cement, using less cement in a concrete mixture is the quickest and most effective way to reduce concrete's embodied carbon. So the question that pops up is, how can you reduce the amount of cement in concrete without reducing its strength? This can be done by replacing a portion of cement with supplementary cementitious materials, or SCMs, from non-fossil fuel-based resources. Using larger aggregate can also allow you to lower the ratio of cement to the rest of the mixture. Examples of SCMs are glass pozzolan, or recycled glass, and rice husk ash concrete. Rice husks are mostly silica and already a manufacturing byproduct. There are more ways in which concrete can become more carbon smart, including carbon sequestration, injecting carbon into concrete during the mixing process, and specifying hard, clean aggregates. Besides details on specifying carbon smart concrete, there are also design strategies that can be employed that will result in less overall concrete in a structure. One suggestion is that if you're using structural concrete, consider also having it be the finish so you aren't creating more embodied carbon with an additional finish material. Also, when considering the building's life cycle, you can plan to have the concrete crushed and reused as road bases and infill materials. There are more suggestions as well as additional resources available on the webpage. When it comes to steel, the best way to reduce the carbon footprint is to specify steel produced from electric arc furnaces as opposed to basic oxygen furnaces. Electric arc furnaces can't process raw iron ore, so they must use 90 to 100% of recycled content. As I mentioned earlier, recycled steel has a much smaller carbon footprint than virgin steel, while still having equivalent strength and performance. The other benefit of electric arc furnaces over basic oxygen furnaces is that they're powered by electricity instead of burning coal or natural gas, and electricity can potentially be derived from renewable energy resources. It's important to specify steel in hot rolled shapes like wide flanges, angles, channel shapes, and rebar because these are the shapes that can be manufactured by electric arc furnaces. Otherwise, reducing the carbon footprint of steel is largely a design issue, designing for less steel overall and using appropriate sizes, and avoiding over-engineering. Overall, gypsum board or drywall is an energy-intensive product. The main ways to reduce the carbon footprint of gypboard in your project is to specify lightweight gypsum, meaning it uses less material and less carbon to be transported, and to eliminate waste material. Strategies for eliminating waste are to model your gypsum boards in your project in order to optimize the amount, and to specify not only the thinnest gypboard possible for the project, but to specify as few types and sizes of gyp as you can, because some different types of gyp cannot be recycled together. You should also have a plan in place for recycling any waste from the construction process, as recycling locations can be difficult to find. And finally, if possible, plan for deconstruction and reuse by specifying battens or dry joints. To understand the amount of embodied carbon for a specific material, there must first be a life cycle assessment. I've already alluded to this concept, but again, it's a methodology for assessing the environmental impact associated with the material throughout its life cycle. This image shows the stages of a full life cycle assessment, often called cradle to grave, or even cradle to cradle, where a material is then reused. These stages are extraction, manufacturing, distribution or transport, use, and disposal. One type of life cycle assessment that may be used is cradle to gate. This life cycle assessment takes only the stages extraction, manufacturing, and distribution into account. Life cycle assessments, or LCAs, are used to create environmental product declarations, also known as EPDs. EPDs are documents that communicate the environmental performance of a particular material or product. To create an EPD for a product, a company must first perform the life cycle assessment on that product. The life cycle assessment that is used for EPDs is cradle to gate because that is the life cycle that the manufacturer is responsible for. That life cycle assessment can be performed in-house or by a consultant, but it must be verified by a certified third party. The main database for EPDs is the International EPD System. On their website is a list of certified organizations and individuals who can verify a life cycle assessment. After the life cycle assessment, an EPD is essentially a transparent report of standardized values for that assessment. Those values can not only be read by anyone, but compared to other similar products. Each product or material falls under a specific set of product category rules, or PCRs. You can think of the PCR as a standardized LCA recipe with boundaries, units, and definitions for a particular product type. Because there are several verifiable stages and standardized methodologies, environmental product declarations can be confidently compared. EPDs can be about specific products or averages of a product type, or a generic product, they might say. These generic EPDs are useful in the design process to help you choose what construction system to go with. This image is a table for the industry average EPD of ready-mix concrete. At the top, you can see that the results are A1 through A3, meaning the stages of cradle to gate. The top line of values outlined in red are the embodied carbon values. The unit for embodied carbon is kilograms of embodied carbon, and in the table, this value is referred to as the GWP, or global warming potential. The other values in lower rows are more specific types of environmental impact, like ozone depletion potential and acidification potential. The different column values are concrete mixes with different percentages of supplementary cementitious materials. And after the minimum and maximum column, the first is a ready-mix concrete with 0 to 19% fly ash, while the far right column is for greater than or equal to 50% combined fly ash and slag. You can see from this table the difference in embodied carbon. The more supplementary cementitious material is used as a replacement for cement. This system may seem complicated and overloaded with acronyms, but the purpose of all of this is to create standards that the whole world can follow, so we really know the true embodied carbon of any particular product. Environmental product declarations are voluntary, but the incentives for companies to create EPDs are to have a competitive edge in an industry that is becoming increasingly more environmentally conscious, and that EPDs are important to all major environmental certifications. With all these EPDs, LCAs, PCRs, and GWPs, it may be easy to say, this is too complicated and I don't have time to learn all this stuff and incorporate it into my workflow. But it's actually simpler than you may think. EPDs are the responsibility of the product manufacturer, and the documentation is available to everyone, so it's just a matter of finding that one number for the product that you're specifying. Because that number is readily available, it's up to you to know how much of the material is in your design. The easiest way to know how much material you're using is to build an accurate 3D model. This model is based on a real project in Fusato, Japan, by Studio Kochi Architects. But simply being 3D isn't enough. It needs to be a BIM model. Building information modeling means that 3D objects have data attached to them. This model is made up of smart objects that the software recognizes as walls, windows, doors, slabs, etc. Unlike extrudes or generic volumes, these objects have components and data embedded in them. That data can be accessed in multiple ways. This is the model with some of its data visualized. Particular values in the walls and doors are set to have a specific color. That color is then applied to the object when the data visualization is turned on. This live data visualization can be used as a design tool, so you can better understand your model at a glance. You can make changes to that data and see the object's attributes update. This data visualization is the fire rating of each wall and door. You can see the values with different colors assigned. The fire rating of a wall system may not be especially relevant to today's presentation, but materials that make up that wall are relevant. Here's a close-up of a wall object selected. You can see in the object info palette at the top right, the object is a wall. It has a class or classification, a layer or location, style or type, thickness, and height. Here is more information about this wall. It has 3 components. Each of these components has a thickness, a height coordinated within the wall system, and a material. Because each component has a specific thickness and height, its volume can be calculated accurately. This wall style is a resource in this document within the resource manager, and that means it can be easily propagated within the file and used with other files via a shared library. It's quick and easy to build models with these wall styles because the information and complexity are baked in. You simply need to draw the path of the wall to get all the necessary information into the model. The materials that are applied to the components are resources within the software that have, likewise, data built into them. The previews of the materials show their attributes, their texture, 2D fill or hatch, and surface hatch. When you go to edit the material, you can see that there are tabs for multiple data types: attributes, construction, physical, and custom. In the construction tab, you see that the material can be reported as an area, a volume, or both. Classification data, as well as product-specific data, can be added here. In the physical tab, you see all the different physical attributes that can be reported, including embodied carbon. Many materials come with embodied carbon values by default. These embodied carbon values are based on the generic EPDs for that material type. Since this material is a resource, you can access it in the resource manager. And from the resource manager, you can edit the material, apply it to an object, or share it with other files. When this material is applied to objects like wall components, curtain walls, and slabs, all that information goes with it. Because that material information is a part of the model, its quantities can be reported. This shows some of the default schedules available in the software, including an embodied carbon calculator. This embodied carbon calculator is based on cradle-to-gate embodied carbon values. This calculator has instructions on how to report materials in your model, even materials with multiple components like reinforced concrete. This calculator also includes ways to calculate the additional embodied carbon from the material having to travel from its distribution location to the project site. The great thing about material resources is that they are flexible. When it comes time to design a new project, you may want to use embodied carbon as a design tool to help you make decisions on wall systems, program, and overall square footage. You want to be able to model a design quickly and get estimates on embodied carbon without having to create all your wall types or floor systems. This is where the flexibility comes in. This is another small residential project, but the interesting thing is it isn't modeled with walls, doors, and windows. It's modeled very quickly using generic 3D modeling tools. Even though it isn't built from smart objects, its volumes and material quantities can still be reported. These are the materials that make up this massing model. You can see that they are concept materials, and there's a small icon at the bottom right. This indicates that they are compound materials. Compound materials are typically used for systems like insulated wall studs and reinforced concrete, where multiple materials might occupy the same space in the component of a wall or slab. It doesn't necessarily make sense to model rebar in order to get a correct volume. Because reinforcing is relative to the amount of concrete, it can be calculated as a percentage of the system. You can see in this concept material there are multiple materials listed: brick, block insulation, gyp, even an air cavity. Each material has a percentage next to it, indicating its percentage within the compound material or wall system as a whole. This concept material is modeled off of a typical wall system, and the materials that make it up are already resources in the resource manager, so it's pretty straightforward to build this system. In the model, this material is applied to the extrudes meant to represent the wall. This means that even in this early stage where there's only a massing model, wall systems can be faked in order to get an idea of the project's potential material quantities, costs, and embodied carbon. This shows additional information attached to the brick material in the project. This custom data allows you to enter in other embodied carbon factors like shipping distance and waste percentages. Here is the embodied carbon calculator for this massing model. I know it's not legible to see it on the screen, but I want to show the amount of data that can be reported from even a schematic model. Here's a close-up of the calculator that's hopefully a little easier to read. You can see the column near the middle of the sheet shows the total embodied carbon from cradle to gate. All the real materials listed as percentages in those concept material resources can be calculated to give a good idea of what this building's carbon footprint might be. Easily understandable graphics can also be generated from the embodied carbon calculator. You can see the percentages that each material makes up in the building's total embodied carbon. With this graphic, you can see where changes to the materials in the design might change the design's carbon footprint. You can even create multiple massing models and compare them side by side using different wall systems, changing the total glazed area, etc. Building information modeling makes these calculations possible. When objects have data, that data can be reported accurately and quickly. When changes are made to the design, those reports update automatically. This automation makes the added labor of calculating embodied carbon feasible for you as a designer. So far, we've discussed materials and how they impact the environment, but it's also important to consider how the materials in a building impact the occupant. Let's start with insulation. Insulation may not be something that an occupant comes into direct contact with, but toxins and insulation can still affect indoor air quality. It's important that insulation be effective in order to have an energy efficient building, especially in regions of extreme temperatures, which frankly is most regions these days. But that does not necessarily mean they need to be produced using fossil fuels or contain toxins. Here are a few effective insulation materials that contain no VOCs or other toxins. Here's a diagram of the carbon footprint of different insulations. You can see that foam insulations have a very high embodied carbon value, while wool, hempcrete, and straw bale actually reduce the amount of carbon in the atmosphere. The reason that XPS, or extruded polystyrene, has such a large global warming potential is that the blowing agent used in the manufacturing process is over 1,000 times more potent than carbon dioxide in contributing to global warming. In addition, XPS has traditionally contained a highly toxic flame retardant called HBCD. This flame retardant can off-gas into an indoor space. Major manufacturers are transitioning away from HBCD, but their alternative flame retardants have not been studied extensively, so it's unknown whether they are actually less toxic than HBCD. Expanded polystyrene, or EPS, also traditionally used HBCD as a flame retardant. Some EPS insulations also contain insecticide to deter termites, which can be hazardous not only to people but also to bees. Spray foam insulation contains dangerous levels of VOC when it's first applied and before it cures. Once it cures, it's considered to be relatively inert, but any disturbance of the material from renovations or maintenance can release toxic chemicals. Because spray foam is considered inert once it's cured, many tout it as a good product for high-performing buildings, but the EPA states that the potential for harmful off-gassing is still unknown. It's also important to consider that spray foam creates a very tight seal, which may increase energy performance, but may also contribute to poor indoor air quality from lack of ventilation, considering that spray foam released toxins into the space as it was being sealed. Fiberglass insulation is a much better choice when compared to spray foams and rigid foams. All the major manufacturers now produce fiberglass batt that is formaldehyde-free, yet some still use a dedusting oil that is a known carcinogen. So when specifying fiberglass bat, look for products that use vegetable oil as a dedusting agent. Sheep's wool is an excellent choice for insulation because sheep's wool is an abundant renewable resource, as well as being an effective thermal and acoustic insulation. Wool is inherently moisture resistant as well as fire resistant, so it does not need added mildewcides or flame retardants. Wool is a keratin and therefore does not support the growth of mold. Wool absorbs harmful chemicals, so it's not only toxin-free, but it actually improves air quality. And finally, sheep's wool sequesters carbon. Carbon makes up 50% of its weight. The carbon comes from the plants and grasses that the sheep eat, so it also means that sheep themselves are green livestock. As far as thermal performance, wool has an R value of 3.6 per inch, making it competitive with traditional insulations. Hempcrete is not necessarily an insulation, but a complete wall system. It's made from hemp hurd, lime, and a hydraulic additive and installed within a structural support. Lime in hempcrete uses 80% less energy than when used in concrete. Currently, there are only a few manufacturers in the US and Canada that process hemp hurds at the correct quality. Otherwise, they are mostly sourced from the Netherlands and China. From a carbon smart perspective, hemp is already an agricultural byproduct and it sequesters carbon, so it has a negative carbon impact. From a health perspective, hempcrete has no VOCs or other toxins because it's naturally fireproof and mold resistant. It also deters insects and is extremely durable with a viable lifespan of centuries as opposed to decades. Hempcrete has an R value of 2.5 per inch and can create an airtight seal if needed. Straw bale is a method of construction that uses straw from wheat, rice, rye, and oats. It's an agricultural byproduct that is plentiful in the US, making it a cost-effective option when sourced locally. North America grows so much grain that if only 1/10 of that residual straw was used in construction, it could be used to build 2 million homes each year. Straw stores 60 times more carbon than is used to grow, process, and transport it. Straw bale construction has a useful lifespan of 100 years and naturally has a 2-hour fire rating when lime plastered. When stacked on its side, straw bale wall assemblies are about 18 inches thick and have an R value of 30. The important thing to note about straw bale is that it's only suitable for dry climates. In climates of persistent humidity of 70% or above, dry rot can develop if the system is not allowed to breathe. When it comes to poor indoor air quality, the biggest culprits are usually finishes, sealants, and adhesives that are used within a space. When it comes to tile, cement-based, additive-free thin sets and mortars are the least toxic. This is a mixture of cement, sand, and lime. Thin sets that contain additives like polymers can off-gas. Non-toxic thin sets and mortars are relatively easy to find, but it's still important to specify them in order to ensure harmful chemicals aren't added to a building's interior unnecessarily. Non-toxic grout sealers, on the other hand, are difficult to come by, but they do exist. There are sealers that are formaldehyde-free and zero VOC, but not many. One of the biggest contributors to poor indoor air quality is paint. Since paint coats nearly every wall and ceiling in a space, it's ubiquitous and in direct contact with the air in the building. Paint also has traditionally had high levels of VOCs that not only off-gas when paint is wet, but persist in the air long after the paint has dried and cured. Both latex and oil-based paints contain VOCs, but there are many brands of latex paint on the market that are zero VOC. I've been using the term zero VOC quite a lot in this presentation, and I should probably qualify it. The label zero VOC, particularly when it comes to paint, does not necessarily mean that a product is completely devoid of VOCs. It means that the level of VOC in the product is below 5 grams per liter. Even so, levels of VOCs are much lower than traditional latex paint, making zero VOC paint a good option. There are, however, truly non-toxic paint options that are all mineral paints. Examples of mineral paints are milk paint, clay paint, lime wash, and chalk paint. Milk paint is one of the oldest known types of paint, and it's made from milk, clay, and natural pigment, making it non-toxic and biodegradable. Milk paint is purchased as a powder and must be mixed with water right before applying. This makes it more labor-intensive than traditional paint, and poor mixing can result in lumps and a streaky finish. It must be used within 2 days of mixing, and it also must be sealed. Sellers of milk paint often have non-toxic sealants as well. Because the pigment is natural, there can be variations in the color, but this doesn't necessarily have to be a disadvantage. The paint has an iridescent quality and can achieve some really interesting finishes. The other mineral paints have similar non-toxic ingredient lists. Clay paint tends to be thicker, almost like plaster, and therefore has a tinted natural appearance like adobe. Chalk paint has a matte finish, but often doesn't come in a wide variety of colors. Most of these paint types have unique finishes, making them exciting and non-toxic alternatives to traditional latex and oil paint. Having discussed so many different materials and strategies for achieving low carbon, non-toxic construction, I want to end on some projects that put these principles to use. The first is the Hawk Mesa Retreat by Jeremy Levine Design. This project is 1,200 square feet, is a 1,200 square foot vacation home in the Mojave Desert. The interior is finished minimally with polished concrete floors, reclaimed wood, and painted gyp. The structure of the building is light steel columns and beams, and the exterior is finished with fiber cement panels and more reclaimed wood. Overall, the material usage is minimal, even with the more extreme weather conditions at its elevation of 4,800 feet. In addition, there are several strategies employed to lessen the building's overall impact on the site, including passive heating and cooling and gray water management. With solar panels installed, the building will reach net zero carbon. The next project is the Watershed Strawbell Residence by Arc and Tilt Architects. Arc and Tilt specialize in strawbell construction as well as other sustainable construction methods. David Arkin is even a contributor to the 2030 Palette website. Earth block was used for the foundation and other masonry. This masonry is made with 65% less cement than traditional CMU and is made from limestone and clay with locally sourced recycled concrete as aggregate. The non-foundation walls were built with strawbell construction, and all the wood used, both structural and finished woods, was sustainably and locally harvested by the neighbor. And finally, here is the Tesla Model Home by Kipnis Architecture and Planning, designed in concert with Tesla and Next House Alliance. This is a speculative project that would showcase the Tesla ecosystem. Some of the green material features include locally sourced wood that is FSC certified from sustainably managed forests and free from VOCs and formaldehyde, as well as zero VOC paints, sealants, and adhesives. Low carbon, petroleum-free insulation, counters, and tile with a high level of recycled content, special drywall that actually removes formaldehyde from the air to improve indoor air quality, and the concrete mix is injected with CO2 to permanently capture recycled carbon dioxide. Sustainable construction should no longer be a specialized practice. We as designers should be doing our part to reduce global emissions and build safer, healthier spaces. The beauty of the projects in this presentation shows that green building practices don't have to mean compromising on design or aesthetics. Designing sustainably means thinking about a project on multiple scales and as a fully integrated system. A systems approach calls for data-driven workflows that allow us to efficiently iterate and optimize our designs. There's a lot to learn and discover as an industry, but with concerted effort, we can all embrace sustainable construction and help limit the effects of global warming. Thank you for your attention, and now I will open it up to any questions that you may have.
Thanks so much, Sarah. So we have about 10 minutes for questions. I'm going to start reading some from the Q&A section. So the first question is from Andrew. Is EAF produced steel readily available in the US or even common and competitively priced?
Yes, actually, it's pretty common. It's one of the few things I talked about that is both common and comparatively priced. It's becoming the dominant method of producing steel.
Cool. Another question. Are there good resources or methods for finding the shipping location of materials? It's one of the more important factors, but the supply chains are quite opaque. How do I know where my gypsum board is coming from, for instance?
Uh, yeah, it isn't that easy. I would say that manufacturer websites usually do have at least some information as far as where their facilities are. And the as I mentioned a couple times, the Architecture 2030, Materials Palette 2030 website are really great with giving you as much access to that information as you can, and then giving you lots of links available. One other thing I would say is I find that this is one of those good uses for AI as far as trying to find this information. I find it's a lot easier to use these tools to find these things where it works a lot better than it used to be just searching on your own.
What type of sustainable design advantages can BIM provide with regard to surrounding demographics, environment, and forecasted development, whether commercial or residential?
So, there are a lot of resources, particularly what I can think of off the top of my head is ArcGIS gives a lot of demographic data based on location. And that kind of data can be easily imported in Vectorworks, for example, there is a direct connection to ArcGIS. So you can download that data and have that available in your model. As far as analyzing and optimizing that data, it's still a manual process, but having that data available and knowing exactly where you're starting from in your model is definitely achievable.
Um, how do the various installations that you showed on the slides, okay, so this question is from a fireproofing standpoint. How well do the installations that you showed on the side perform? The question is whether fiberglass and mineral wool, yeah, in relation to fiberglass and mineral wool.
They all actually perform pretty comparably to standard forms of insulation. And you can definitely find all of that information on the Materials Palette website. That's the probably the best place to look for alternative materials, and it will give you all of that relevant information.
There's a question about staining. Can polished concrete stain easily in kitchens and baths?
Um, Yes, I mean as I said, like sealers are one of those things where it's a little more difficult to source zero VOC products, but they are out there, and both like manufacturers and even more kind of standard places where you yourself could go shop are really um, starting to provide more options for zero VOC products. I mean, just in the last 4 years, I've noticed how much easier it is to find something like zero VOC paint. So yeah, those kinds of sealants are there are different products available that can really be a lot less toxic than traditional sealers.
Can you talk more about how to use AI to find information from the manufacturer, such as sourcing? And do you have any preferred apps for using AI?
Yeah, I like using Perplexity. I think it's a really good search uh, engine. Like it tells you what websites it's mining from when it's finding that information, which is a great way to just to then go directly to those websites. That's how I find that it works the best is you ask your question, where does JIP come from? Where are the supply chains for JIP? And then it will give you, it may not give you the exact answer you're looking for, but it will cite its sources. And that gives you a great way to then do your own research and verify the information that you have. Um, yeah.
In countries that have more of a usage of concrete in relation to wood, how do we reduce the carbon usage and what methods can be used to do so?
When it comes to concrete, it's really about the easiest way to lower the carbon footprint is to specify supplementary cementitious materials. So this is something that's pretty widely available when it comes to specifying concrete. It you usually have a lot of opportunities to specify that type of concrete. But then things that are more more sustainable are carbon sequestration methods. These aren't as readily available right now, but there are a lot of companies that are coming up with different techniques for doing this. And I think that this will be kind of the next thing that will be done with concrete. And so hopefully those types of concrete curing methods will become more widely available.
Great. So those are all the questions we have. Sarah, is there anything else you'd like to add before we wrap up?
Just another plug for the Architecture 2030 website. It really is the best place for you to go to get more information. It's a really well organized site. So
Cool.
yeah.
Well, with that being said, I'm just going to give some closing words. Thank you all so much for attending the live webinar, Enhancing Sustainability Through Materials in BIM, a CE Strong webinar series powered by the Architects newspaper. This presentation was sponsored by Vectorworks. This webinar is recorded and can be easily replayed using the same registration link. Please allow 7 business days to process certificates of participation and area credit reporting for this presentation. A big thank you again to our presenter, Sarah Walker, and to Vectorworks for sponsoring this webinar. We hope to see you all again at our future event. Have a great day.